Okay, I think we can get started, and today we are going to finish talking about turbulence and the effect of turbulence on aerodynamics, and then if we have time we'll go into Mach number and the compressibility. Alright, so last time we are stuck on this question for a little bit, and this time I'm going to break it down for you a little bit more so that like we're actually going to start continue working on the problem. But so here's kind of a breakdown of the steps to get the final answer, which is I'm asking you to sketch qualitatively the velocity profile Vx as a function of y, right? So we're going to do this in 4 steps. First of all, sketch the shear stress as a function of y. That is basically using the same kind of control volume analysis we did last time. So the first case is easier, so do it the first case first. And then we already gave you the formula for the turbulent viscosity, right? So you should be able to sketch the total viscosity as a function of y. And then, because we know the shear stress is the product of the total viscosity with this velocity gradient, you should be able to sketch the velocity gradient, right, as a function of y. And finally, you know the velocity gradient, and you also know the boundary conditions, which is the velocity on the top wall and at the bottom wall. So you should be able to sketch just the velocity profile, okay, as a function of y. So let's get started, and I hope yeah, you can do it yourself this time. All right. Here. Oh. Yeah, shear stress is constant. That's basically from conservation of momentum, right? A balance of force balance for the first case. For the second case, shear stress is not constant, but let's work out the first case first. Yeah, same problem. I won't continue before you work it out.
Sorry?
I won't continue until you work it out.
Yeah,
so work it out.
I see that.
Yeah. No, Vx is a function of y. Yeah. Or maybe I can add a 1.5. So 1.5 is basically sketch d as a function of y, right? Because d is the distance to the nearest wall, and your mu t depends on d, right? So sketch is basically draw it. So what is your sketch for tau?
We haven't done that yet.
Okay. I mean, so it's essentially the same as last time, right? So we did a conservation of momentum analysis.
Yeah.
The shear stress of here has to be the same as shear stress over here.
Yeah.
So shear stress has to be a constant. So if you always draw this as y and this as tau, it has to be like a straight line,
Oh, okay.
right?
Yeah, that makes sense.
So that's like what I mean by sketch the shear stress.
Okay.
Yeah, so d as a function of y, like if you look at the distance, right? And this is 0, this is, I think I called it h. Yeah, what is the wall distance as a function of y? So when y is 0, what is d?
0.
0, yeah. When y is h, what is d?
H.
No.
Okay.
The distance to the nearest wall.
Oh, 0.
0, right? And in between is something like that. Right? This position is half h. Because it's equal distance to the both walls.
Oh.
So that's what I mean by sketching things. Yeah.
D itself is oh, well, you're saying like the full definition of tau. Oh. No, you're good. Okay, I see what you're saying. Okay, yeah. So it would be like 10y plus h.
Yeah, I still don't see people starting to sketch things. I just want to make an example of what I mean by sketch things. So for the first question, right, we know from a conservation of from a force balance, we know the tau has to be the same no matter where you are, right, at what y location. For the first case. So if I draw, if I sketch y being the y-axis and the x-axis being tau for the first case, right? I would just do a vertical line because I know wherever y is, tau is going to be the same. So that's going to be my sketch, right? Does it make sense? So at the bottom is y equal to 0, at the top is y equal to h. And the sketch for tau is basically a straight vertical line. Does that make sense? Oh yeah, here I see you have drawn correctly the second question, actually third question now. The total viscosity as a function of y, so that's good. All right.
There's only shear force, no pressure gradient.
Questions?
And the flow is the constant velocity.
Yeah, this is right. This is the distance, right? The distance would be 0 and 0, but maximum over here. Yeah.
The only forces are shear forces. And so tau on this face has to equal an opposite tau on that face.
Okay, so which question are you trying to do now? Question 3?
Wait, question 2.
Question 2 is the distance, is the wall distance, and I think you draw the shape here correctly, right? Yeah. Wait, 1 second. So why is this?
Well, if you like escape, if you're outside here, you're no longer feeling the shear stress.
Oh, I see. D greater than half h. Okay. Mu times this. And you have to multiply with the dy. Yeah, times the dy. Yeah, that's right. Sorry,
I think it might still be inside the pipe, but in the top half.
yeah, you're gonna be when you're at the top half, you're still inside the pipe. So what I would recommend is instead of directly doing this, first draw. You already sketched the tau, right? What is the sketch for D? Yeah, that's right. Yeah, this is the maximum, right? When it's exactly right. Okay, so once you have D, just draw the turbulent viscosity, or just draw the total viscosity, mu plus mu t.
Okay,
which is this thing, yes.
Yeah. Oh, and we're just drawing this here in our control volume? Is that what you're saying?
Draw wherever, whichever plot you draw. You can have y being x-axis or y being y-axis, it doesn't matter. Like, I can interpret the plot either way.
Okay. Wait, which quantity? Sorry, am I plotting again?
Total viscosity, mu plus mu t.
I think it will start at some constant and just like mirror the shape.
I think it starts at 1, right?
Yeah.
Yeah, starts at 1.
Static.
Yeah.
Okay.
And then I think it would have the same relationship as D.
Yeah, it has the same shape, but it goes to, I think, 11 times or something. No, actually 6 times, right? Yeah, because D, the maximum D is half H.
Over 2, so
Yeah,
5
so-
plus 1 is 6.
Yeah, 6 times. Yeah. Exactly. Yeah.
Thank you.
And then afterwards, would it just go back to
So this is which quantity are you trying to sketch? D? Yeah, so D is the distance. Okay, so are you thinking y? Which one is y? I mean, either way is fine. Just decide which way is more intuitive to you. This one is y, okay? Right. So if this is D, y inside the channel goes from what to what? Goes from 0 to what? H, right? So when y is equal to 0, what is D?
Yeah, so isn't it just the slope?
D is the distance to the nearest wall. Yeah, 0. That's right. Because y equal to 0, I'm 0 distance from the bottom wall. When y is h, what is D? Also 0, right? Okay. And where is exactly? So that's why I'm saying this plot is correct. And what is this? What is this value? Half h, exactly. That's the plot. Okay, so now like the total viscosity, right, is mu plus mu t, which is mu times h tan d, right? So basically, then try to draw this as a function of y. Yeah, this is good. What is the top value? H over 2, yeah. That's right. Good.
So for a given time, we would have this, which is this.
Oh, the question said to sketch it as a function.
Because how also would we get the d dy? I mean, we plot this in order to get d dy, and then we can sketch it.
Oh, so you're just using this to...
Get the
Yeah, so what are you using to get du dy?
the shear stress versus the
Exactly. So it's basically this plot divided by this plot, right? Do you have a sense of how to divide the two plots?
But that one is bigger than
Exactly, yeah. I mean, the numerator is a constant, right? So it's basically the reciprocal of the plot that has the triangle in it.
the reciprocal of this.
Exactly, yeah.
Or do you get the intuition right now?
This is the okay. So this is the linear function of this, right?
Well, no, why? How do you even?
It's a constant plus something. Exactly. Yeah, right. Oh, this is correct.
Are you sure? Oh, yeah.
Which one are you trying to do now?
We're doing the 4 and 5, but for the second.
Oh, for the second. Okay. So for the first picture, what is your?
These 5
So this is 3. Where is your 4?
right here. Yeah.
No.
Okay.
So how did you get dv dy?
A derivative of a linear line.
No. So these plots are for laminar flows, right?
Oh, okay, yeah.
Yeah,
No,
so
we were just
basically-
considering that.
Yeah. Don't. I mean, these are just the first sketches of what the problem looks like. The
Okay.
figure above shows the velocity profile of a laminar flow. Now you want to consider turbulent flow. So you have this, right? Tau is equal to this times this. You already have a plot of this. You also have a plot of this. So, how about this?
It's
Exactly, it's this plot divided by this plot, right? So can you try to, in your mind, divide this plot by this plot and see what it looks like? Yeah, sorry, divide this plot by this plot. Yeah.
wow. This is a constant value, no?
Yes, the first question is a constant value, so that makes the division a little bit easier.
So it's like a line.
It's going to be a reciprocal, right? I mean, how do you take a reciprocal of this plot? Okay. This is good. This looks very good.
This is right?
Yeah, this is right. Okay. Yeah, this is very good. All right. Yeah. So basically, near the wall you have steep gradients, right? In the middle, where you have large viscosity, you have a lot shallower gradients. This is like basically everything you see in turbulent flow is like that. Near the wall you have steeper gradients. Away from the wall you have shallower gradients. Compared to laminar flow, it's always like the case. Yeah, this is good.
Okay.
This is also good. So you have.
I kind of overheard you saying this part. How do we actually, like, this might be a very dumb question, but how do we actually know that the shear stress is constant here?
So basically, by the control volume analysis, there is only shear stress acting on the right.
Right.
Like the force acting on the control volume is just the shear stress. So
Oh,
the
and
shear
it has
stress from the
to-
top has
okay.
to balance the bottom.
Right. That makes sense.
Yeah.
Okay. That makes sense. Yeah.
Okay, so now you're working on the second.
Yeah.
Okay.
I don't know
Yeah,
if we
this
know
is
how to
this is roughly
divide.
right. Yeah, that's the shape is right. I mean, it's not exactly linear, but like
Yeah. So like this is why? Because we flipped our.
yeah, that's right.
And then that's dv of e.
Yeah. Yeah.
So you said it's not directly linear?
Yeah, because the reciprocal of a line is almost like it's like the 1 over x shape. So it'll be curved like yeah. Not exponential, but something like that. Yeah, that's right. That's right. Something like that.
Oh.
Yeah.
Okay.
So this is exactly what it looks like. Yeah. Oh, you that and where is this is not correct. So how did you how do you think get dv/dy? So the plot I've drawn there are velocity profile for laminar flow, right? So you cannot take the velocity profile and take derivative. So now consider laminar flow. How do you think you're going to get
Origin is here.
dv/dy?
For this problem. Yeah. That was the confusion from before. Oh, I see.
Yeah, I thought it was.
Do you remember the formula for shear stress? It's equal to the total viscosity times dv/dy. So here you plotted the total viscosity somewhere, question 1, right? You plotted the total viscosity, which is here, right? And you also know that the shear stress is a constant. Yeah, if you write it down like tau is equal to mu plus ut, which is plotted here, times dv dy, right? So you have a plot for this, you know this is constant.
This is not.
So can you try to plot this?
It's telling me the opposite. Of course, the gradient is not.
What shape multiplied by this would get you a constant?
I'm not sure.
Working on the same problem right now.
Okay.
We have the governing equation here.
Yeah.
We know
You
how
know
many
this.
changes.
Yeah, you also know this is a constant. So what kind of a plot multiplied by this would get you a constant?
1 over that.
1 over that, right? So when this is higher, your plot has to be lower. When this is lower, your plot has to be higher.
So it'd be like
Yeah. It's not exactly linear, but like also it doesn't get to 0, right? Because 0 would get you 0. So yeah, just refine it a little bit. But this is roughly the shape. Yeah, this is correct. This is good. Oh, okay, Desmos helps. Yeah,
I was
that's
gonna, well, 'cause I was trying to use it to just divide. I was gonna divide
Yeah, that's-
like
that's right.
divided by y,
Yeah.
so then it would look like that. The green, right? For dy.
Wait, so since the derivative is
So these two lines are not exactly what you have in plot 3, right? So your plot 3 is shifted up a little bit.
Yeah.
So if you just plus,
then we can just sketch it.
I don't know, point 2 or something, point 3 or something,
H is equal to
then
since at the wall there's a no step.
wait, you have two y's. Which y is this?
Yeah, I was
Relative to the board, yeah.
to get
But
both
relative to
sides.
the
I was gonna put a limit.
rest frame, I just
to
tell
it.
you B0.
Yeah, anyway, so if you just cross this one,
In the setup
What?
of this problem, this thing is moving.
Yeah.
Okay, I didn't have to.
I think it's equal to m plus.
Or not.
Yeah, actually don't really. M is the x-axis.
Yeah, I just picked on a letter. You can change it to x.
Let's see. Like that. No.
Is there a way we could get a coordinate to this?
I think y is actually reserved, so if you just use f, that'll get you the right function. Right, so it goes down like that, and the other one you have to go up, symmetric.
Oh, you're saying, okay, like an actual number.
Then I feel like
Or you can just think about it, right? So when the mu total is large, your dv dy has to be small. When mu total is small, your dv dy has to be large. So it's going to be a plot like that and then go up. Yes, exactly. Yeah. And that has to be symmetric on both sides. Yeah. Got it? Yeah, that's right. That's good. So now you have dv dy, right? So how do you get to v? So basically you have to draw a curve whose derivative is high at the both ends and low in the middle. So imagine what kind of curve would match that. Okay, you're also working on this. What kind of curve would match a derivative like that?
Where it's very low or very high at the ends and low in the middle.
Yeah. That's like visual calculus. Oh, that's good. That's good.
Yeah.
Exactly. Yeah.
Yeah, it's like something like that.
Yeah.
It's cubic.
Huh?
A cubic function, basically. Or
Yeah. Yeah.
It's a little scuffed. But
Yeah, that's right.
and then basically for both cases, would it just be then smoother for the other one? Or?
Yeah, so I mean, just imagine like near the walls, the velocities are steep, right? Away from the wall, the velocity are shallower.
I see. For both cases.
For both cases, the other case you can also work it out, but like the principle is the same.
How's our last graph look? So we
Where is
like
your
one
last?
of the x for
Yeah,
this
that's
one,
right.
And then we did like ln of x.
You
Right
did
on.
what?
We're trying to integrate it.
Wait. So you need to draw a velocity profile whose derivative is that.
Derivative.
This is dv dy, right?
Yeah.
So you need to draw a v versus y. The derivative of that function is that.
Yeah.
And is dv dy positive or negative here? It's positive everywhere. So the slope of this has to go up everywhere, right?
But the top ones are integral, right? Like we integrated this.
Well, I'm just saying you integrated incorrectly.
Oh yeah.
Because if you integrate it correctly, the derivative of the integral is actually this, right?
So it's just a cubic. Are we just looking at a cubic? Right.
Something that looks similar to a cubic, actually.
Okay, that's
Yeah.
Okay, fine. But it just needs to be positive at all points.
Yeah, it has to be positive at all points, and the slope is high here, and low here. Exactly, that's something.
Low, high,
Exactly.
all positive. Oh, valid.
Yeah, you need to learn visual calculus, right?
Visual calculus, you have to learn that.
Yeah. Okay, can I walk over?
But we don't, and then we force that down.
Sorry, what is your, where have you walked through yet? Do you have the shear stress as a function of y?
Or shear.
Yeah, start.
We did it through the forces. We used this thing.
Yes?
We forgot to do that.
Okay.
But and then because this is almost the same thing, but like 1 degree more than in the first case. In first case, we had this shear stress is constant, and we were dividing by this.
Now the shear stress is.
divided by this, so this has the same shape as this thing. No, just minus because this thing is negative.
How did you get this? I don't think this is correct.
From this equation.
And how did you get this equation?
Force balance. It's a second case.
Where did that come from, though?
The pressure and the shear.
Yeah, can I? Okay, so the correct equation is dy mu plus mu t dv dy equal to. Yeah. So in the previous question, there is no mu t, right? So I can pull this mu out, and that gives you that equation. Yeah. So I didn't. So I didn't ask you to actually derive the differential equations. But if you plot what is the shear stress, I mean, this is going to be the shear stress, right? The shear stress has a derivative that equals to a constant. So the shear stress is going to be, if you plot y and the shear stress tau, it's going to be something like that, straight line. Okay. Yeah, dpdx is negative, right?
Yeah.
So that's going to be your shear stress plot. And then the plot for mu plus mu t is going to be exactly the same, right?
Yeah.
So you're going to be dividing this by this.
I see.
Okay, and you're going to get something that's after the division, you should get something that's like a lot larger over here. So basically something that's like that.
I mean, that's kind of what we have here. Just shift it down.
Yeah.
I really, that's interesting.
Yeah. So then if you construct a function vx that has a derivative that matches this, and so then you can compare against the laminar case. The laminar case has a straight line, right?
Yeah.
And if you compare this, you're going to get a velocity profile. So the laminar is exactly a quadratic, right? This guy has a much higher derivative here, much lower derivative closer to the middle. So you get something like more like that. That's kind of the yeah. This is the second one is harder. Okay, so let's get back to our seat, and I can walk you through a little bit down all the questions. I think some of you, or most of you actually got the first question all the way to the end, right? And the second question is similar, but you need a little bit more kind of a visual intuition for calculus, like derivatives and dividing two functions to be able to plot it. But like I'm sure, like if you work on any kind of a physical disciplines, engineering, over time, you should be able to build this intuition of, okay, so if I have two function plots, if I divide them, how the resulting function looks like, right? And if I have a function that looks like this, what does the derivative looks like? And if I have a function whose derivative looks like something, you plot what that function looks like. So all of these are intuition, I think, you should build over time. So for the first question, the shear stress looks like a constant. And for the second question, I'm just going to draw it over here. So for the shear stress, it'll be y and also h. And if this is tau, the shear stress would start positive at 0 and becomes 0 in the middle and becomes negative at h. So this is what the shear stress will look like. Okay. And the reason for this is again force balance. If you draw a control volume in the middle, the shear stress imbalance from here to here has to be exactly proportional to the height, because the amount of pressure gradient force, the amount of pressure force is proportional to the volume, right? To how high the difference is. Which means the difference in the shear stress has to be proportional to the height, and that translates to this linear profile. I mean, the linear profile basically meaning the difference of the function between 2 points is proportional to the distance in the y-axis, right? So the distance in the tau axis is just proportional to distance in the y-axis. That's a linear function. All right, make sense? Okay, so that's first question. And the second question, d as a function of y. So if I say this is d as a function of y, of course, I think you all draw it correctly. So basically it goes from 0 to half of h, right? So this is d as a function of y. And as a result of that, if you plot mu plus mu t as a function of y, is basically just a shifted version of this purple line. The shift is basically because there is also a laminar viscosity added on top. Alright? Okay, so now the most difficult question I think is when I'm taking the reciprocal, because tau is equal to mu plus mu t times dv dy, dvx dy. So dvx dy is tau divided by mu plus mu t. So for the first case, means always the green line divided by this orange line, right? For the first case, I'm just taking the reciprocal of the orange line, and I'm going to get something like that. So that's going to be my dvx dy. So for the second case, I'm taking the green line and then divide by this orange line. So I'm going to start with something negative. So here is a large negative value divided by a small positive value. And as the green line goes to 0, the denominator also increases. So I'm going to get back to 0 at a faster rate than the linear line. So it's going to go like this and then go like that. So this is how the derivative of velocity looks like. Okay, so now finally we're going to get to the velocity profile. This is constructing a Vx whose derivative matches the red line. And in the first case, the derivative is all positive, right? So I have to have a velocity profile that goes up as a function of y all the time, except for the derivative is much higher near the wall compared to in the middle. So I have to have a profile that looks pretty much like that. So instead of a linear profile, I have a profile that is very steep near the wall and shallow in the middle. Similar for the second case, I need the velocity profile. First of all, the integral of the derivative is equal to 0, right? So I have my velocity being 0 at both ends. But again, the derivative is very steep at the wall and shallow in the middle, and then goes back to steep near the wall. So that's what the turbulent velocity profile looks like. And in principle, in both cases, and actually in all cases, my velocity profile is steep near the wall, shallow away from the wall. That's going to be always a natural consequence of the fact that the total viscosity is small near the wall and large away from the wall. Okay? So whenever you have a turbulent flow, that's roughly the case. The regions with higher turbulent viscosity, a lot of mixing, your average velocity profile is going to be shallow. regions where you don't have a lot of mixing, for example, very close to the wall, your velocity profile is going to be very steep. All right. Okay. And other regions, for example, in a turbulent flow where the velocity is very steep, for example, the core of a vortex. I mean, like there is I'm not going to talk about the reason in this class, but like if you study advanced aerodynamics, there are, like rotation, strong rotation actually suppresses turbulence. So in regions where the flow is rotating a lot, for example, in the center of a vortex, turbulent viscosity is very low, and as a result, like the center of the vortex is a region where you have a very high velocity gradient. Okay, that's basically near the wall center of the vortex is where you see velocity having large variation over small distance. And the regions where there is a lot of mixing, large-scale turbulence, you expect the velocity profile to be shallow. Okay. And so here I just want to contrast this is the prototypical or most commonly referred laminar boundary layer. It's called the Blasius boundary layer because Blasius is the person who derived a simple set of equations that the solution of which is this laminar boundary layer with no pressure gradient. And through these equations, he can derive a bunch of quantities. For example, delta 99 is equal to, we already know that the thickness of the boundary layer goes like the square root of x, right? But through the set of equations, you can actually derive the proportionality constant. Okay, you don't have to remember this, but like one thing I do recommend you to remember is actually the ratio between the displacement thickness and the momentum thickness. The ratio turns out to be about 1.72 to 0.665 is about 2.6. So that's defined as the shape factor, right? The ratio between the displacement and the momentum thickness. That's the shape factor. And the laminar boundary layer has a shape factor typically of 2 point something without pressure gradient influence. When you have favorable pressure gradient, the ratio is going to decrease. When you have an adverse pressure gradient, the ratio is going to increase. But this is like the baseline with no pressure gradient. All right. And but then when you have a turbulent boundary layer, things becomes very different. Okay, so before I show you the figure, I show you the video. I'm basically drawing the most iconic difference between a laminar and a turbulent boundary layer. So for a laminar boundary layer, it looks more like this. This is actually the Blasius boundary layer plot. You're going to see like inside the boundary layer, there is a large region where the velocity gradient looks almost like the same. I mean, actually they are not. The velocity gradient always decreases as you go towards outside, but the rate of decrease, the amount of velocity gradient is pretty constant over a big portion of the boundary layer. For the turbulent boundary layer, it's very much not the case, right? As we have derived, the velocity gradient near the wall is very, very high, very steep. And as you go away from the wall, there is turbulent mixing, and the total viscosity increases, and as a result, the velocity gradient decreases. So you typically have a boundary layer profile that goes like that, and then like that. So the velocity gradient is changing like all the time, going from the bottom to outside. As a result of that, it's not obvious, but if you do the math, you're going to figure out that for a turbulent boundary layer, the ratio between the displacement and the momentum thickness is going to be much, much lower than that of the laminar boundary profile. Okay, so by definition, actually you can figure out it's always greater than 1. The shape factor is always greater than 1, meaning the displacement thickness is always thicker than the momentum thickness. But the ratio is much smaller for turbulent boundary layer. It's typically on the range of 1 point something as opposed to 2 point something on the zero pressure gradient. Okay, and if you find a turbulent boundary layer that has a shape factor that's like 2.6-ish, it is on the very adverse pressure gradient. Okay, and potentially close to separation. Okay, let's actually look at. So So another thing about turbulent boundary layer is I want to point out is that just look at these two. Which one has a higher shear stress at the wall? Turbulent one, because the gradient is much steeper at the wall, right? So turbulent boundary layer under the same thickness usually have at least several times higher wall shear stress than laminar boundary layers. Okay, and so this is the first consequence you are going to see is that okay, when the flow transitions into turbulent boundary layers, the friction on the wall increases a lot, and if you care about heat transfer, the amount of heat transfer also increases by a lot. As a result of that, I mean, there are several consequences. One consequence is the drag is going to increase, right? Drag due to skin friction is going to increase. And so that's why like there is a lot of interest in making as big of a laminar portion as possible to reduce the skin friction drag. But on the other hand, we're going to see later that turbulent boundary layer is more resistant to flow separation. Just think about the adverse pressure gradient trying to push the flow towards separation. Basically, the bottom layer coming to zero velocity means flow separation. And it's very easy to imagine, like the laminar boundary layer gets pushed to zero a lot easier than this turbulent boundary layer, right? For which most of the boundary layer has a velocity closer to the free stream. So that's much harder to push against towards separation. So the two consequences of turbulence, I think is important to just know conceptually, is that increases friction and heat transfer. That's one. And the two is more resistant to flow separation. Okay, I think that these are the only two consequences I think you need to know about turbulence, right, in this level of class. Okay, so let's watch the video to gain a little bit of other perspective on the turbulent boundary layers and its impact on aerodynamics.
The boundary layers we have seen so far have all been laminar. However, in most practical high Reynolds number situations, the boundary layers are not laminar. Rather, they are turbulent. Flow along a cylinder filmed with a high-speed camera can show the stages in the transition of a boundary layer from a laminar one to a turbulent one. A slight adverse pressure gradient causes transition to occur within the field of view. The steps in the transition are very complicated and interdependent. Of nearly two-dimensional waves, the Thomaine-Schlichting waves, followed by the appearance and growth of three-dimensional disturbances associated with streamwise vorticity. Then turbulent spots can be seen. And finally, fully turbulent flow appears. Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way. This boundary layer around the channel bend is made turbulent by placing an obstruction in the layer upstream. The obstruction stimulates the naturally occurring processes and hastens the onset of transition. The flow here is all downstream. Removing the trip rod results in separation and backflow. Bubbles accumulate at the separation point. In this diffuser, which was used before, we have made the bottom boundary layer turbulent by inserting a trip rod upstream. The turbulent boundary layer is able to withstand the adverse pressure gradient in the diffuser,
Yeah, this is actually one of the most iconic visualizations of a turbulent boundary layer more resistant to flow separation, right? So, so usually people, they call trip the boundary layer by adding a small disturbance, usually like a zigzag line. That's it requires a very small disturbance for to actually make the boundary layer more turbulent. And well, that's actually one of the reasons there is a lot of difficulty in actually getting flow to be laminar on like real airplanes. Because if the real airplane just hits a bug that attaches to the leading edge, and that can destroy your whole effort of making the flow to laminar as much as possible. So it's really easy to trip the boundary layer to make it turbulent. And in this case, the upper surface is very clean; it stays laminar. The lower surface is tripped to turbulent, and the flow. This is a completely symmetric channel, right? So the flow is going on exactly the same type of adverse pressure gradient as the channel. As the channel widens, right, the flow has to decrease in speed, and what is making the flow decrease in speed is the pressure gradient, right, force pointing backwards. So the laminar boundary layer stays attached, and the turbulent boundary layer stays attached, and the laminar boundary layer separates, right? So this is a pretty typical situation. Okay, let me just say a little bit on that. So that has a lot of consequences in the design of high-lift airfoils. So if you look at two airfoils designed to be high-lift. High-lift means it won't separate until you achieve a lot of lift coefficient. So the first one is designed to get a lot of lift on the laminar flows. So basically, it is typically used for small things going at low speed, right? And on the right-hand side, it is an airfoil designed to be high-lift at higher Reynolds number for bigger stuff. So if you look at the difference, it's very hard to kind of it's very hard to think about why the airfoil look different until you look at the pressure contour. So this is basically this is the lift. This is the pressure plot of these two airfoils on the close to the highest lift. So what you see here is that this guy has a pressure gradient that is steep over here and gets shallower and shallower. The reason is that the designer of this airfoil expects the whole boundary layer on the suction side to be laminar. And a laminar boundary layer, as it gets thicker and thicker, it is actually less and less resistant to flow separation. Right? Remember, the viscous forces are stronger when the boundary layer is thick. The viscous force is less strong when the boundary layer is thick. And viscous forces helps make the boundary layer more equal, right? Make it closer to a Blasius boundary layer. While the adverse pressure gradient tries to make the flow separate, make the velocity, it magnifies the velocity differences, right, between the different layers, as you have worked out in class. Okay. So that's why when the boundary layer is still very thin over here, it is able to withstand a larger pressure gradient without separating. But like as you go towards the trailing edge, the boundary layer thickens over here, you need to put it at the lower and lower pressure gradient so that the flow won't separate. Okay, so that's for this one. Now somebody guess why there is a similar trend here, right? The pressure gradient is very steep here, it gets less and less steep here. But it gets steep again here, and also becomes less steep over here. Why is there a two-stage process? This two-stage process is actually because the designer of this airfoil fully expects the boundary layer to have transitioned into turbulent boundary layer before this point. Okay? That's the reason after this point, it is okay to make the pressure gradient steep again, because once the boundary layer transitions into turbulent boundary layer, it is more resistant to adverse pressure gradient. So basically it is really by tuning the curve. It's hard to see here because this pressure gradient is more sensitive to curvature than slope, right? So I mean, human eye don't really see curvature that well. But anyway, so the pressure gradient is designed to be higher over here, exactly because there is confidence the boundary layer is turbulent over here. But again, a turbulent boundary layer, as you get thicker and thicker, becomes less and less resistant to adverse pressure gradient. That's why the pressure gradient is also designed to lessen over here. So this is basically underlies the design principle of airfoils that is designed to get as much lift as possible. All right. Okay. So another thing, finally, I just want to say another thing is that the trip of the boundary layer into turbulence also can have very interesting effect on the drag over block bodies. So this is a typical curve for how the Reynolds number affects the drag coefficient for block body. In the beginning, as you increase Reynolds number, viscous forces decrease and you get less and less drag. But at some point, the skin friction no longer contributes that much to the total drag. It's the flow separation, right? The flow separation contributes to most of the drag, so that's why it is constant. And suddenly, at some point, the boundary layer becomes turbulent, more resistant to separation, and the separation shrinks. So you get a sudden shrink of the drag coefficient. And then, as Reynolds number further increases, the turbulent boundary layer also have less viscosity, and the separation widens. You get higher drag. But if you trip the boundary layer by making the surface rough, you can have an earlier decrease. Okay, you can have an earlier transition to turbulent boundary layer and earlier decrease of how much drag you have. This is just some interesting fact about not aerodynamic bodies, but bluff bodies with flow separations that can be affected by laminar and turbulent boundary layers. All right, so next lecture we are going to be going to a completely different topic, away from viscous flows to compressibility, Mach numbers, and transonic and supersonic flows. All right. Yeah.
The picture that we were looking at, turbulence, like this velocity thing that is like steeper here.
Yeah.
And this is like, how was that? Like this thing?
Yeah. So laminar and turbulent.
Yeah.
So laminar is more like a straight line and go like that. A turbulent is very steep here, but at some point it becomes less steep and overtakes that and goes back to free stream very slowly. So that's more like turbulent. That's more like laminar.
Yeah, so if you have a very high adverse pressure gradient, can it happen that because of that this turbulent like becomes acts like laminar flow, or?
Can you say again? Sorry.
Like
if you have an adverse pressure gradient
and this thing tries to go this way.
Yeah, so the laminar one goes this way very, very quickly, right? The turbulent one may go. The turbulent one is first going to get closer to the laminar one, so it's going to go like that.
Yeah.
But it's
but it can't act as a laminar, so we can't make the turbulence to laminar flow by adverse pressure gradient.
No.